happy to have Professor Shapiro.
Yeah, thank you for.
Yeah, that's secret.
It's secret part. It's in Russian. Okay, so thank you for invitation. It's a pleasure to talk here. I apologize. I see I kind of repeat this talk several times in Moscow, and I notice there are many people who already listened to some versions of this talk. So
Maybe they did not understand.
yeah, maybe now it's kind of chance to understand it. Yeah, and so it's a project that we do with Leonid Chekhov, who is present somewhere over there. And
In a bad way.
okay, so let me probably start with some hand-waving explanation why I think it's kind of interesting. Yeah, please, I don't know how much you know about this stuff, so if it's familiar, just fast forward me, tell me that it's already known. It's a project about comparing two different objects. One is a kind of algebraic object, and on the algebraic side is, I'm sorry, may I also write in English, because on the algebraic side, it's something which is called symplectic gruppoid. And I will say in a few minutes what it is, and on geometric side is a Teichmueller space of closed hyperbolic surfaces. So both spaces are equipped with some natural Poisson structure, and kind of according to
surface is boundary, right?
sorry?
Surface is boundary in general, right?
No, close.
No, closed means there is no boundary.
Then it has a symplectic structure.
Okay. But if it has symplectic structure, it's even better, so it has like very special Poisson, non-degenerate
If it
Poisson.
has symmetric structure, it has Poisson structure as well.
Yeah.
А вот эти поверхности, это просто можете представлять действие каких-то дискретных групп на плоскости Лобачевского? Да? Время вопрос. Сейчас. Правильно? Или так?
Yes, yeah.
Нет, вообще вроде пока написано, что род больше либерален двух, да?
Да. Но это гиперболические поверхности. And there is a Poisson structure here. It's called Wellman bracket. And also there is natural structure here. Which doesn't have canonical name, and depending on whom you talk to, so it's I will start with Bondalom.
Bondalom Weinstein?
No, Weinstein never pretended that he. Бондалом, Дубровин, Пугавия.
Вообще все вопросы из истории науки можно опускать.
Okay, many other people. And we want to study some sort of nice coordinates with respect to this Poisson structure. So we call them, the name we coined, and it's a very bad name, but anyway, so It's called log canonical coordinates. Idea is that we try to do some sort of Darboux coordinate for Poisson structure, but in algebraic settings it's not always possible. And then we try to replace it with whatever we can do. So the collection of functions.
Слово пока не сказали.
А?
О чем речь не сказали, то есть детали, они, так сказать.
Yeah. So okay. So what I want to say, we want to find some nice coordinates for this guy, and it appears that these nice coordinates simultaneously define some nice coordinates in for Teichmueller space of genus two surfaces, which was unexpected. So such nice coordinates were known when surfaces has boundaries, but for the case of surfaces without boundaries, this construction is new. And big question is, can you extend this construction for higher genera, so for n greater than kind of
So
sort of.
is it true that in some cases you established isomorphism of these two Poisson structures, and this isomorphism is given just coordinate-wise? So there is no natural correspondence. Just you observe that in some coordinate system they numerically coincide.
Numerically, I don't understand.
No, the coefficients are the same of the Poisson structures.
Well, no, there is a map from there is Poisson map from Teichmueller space into this setting,
Which is given coordinate.
Coordinate free.
No, it's given in coordinates. Yeah, so it's given in coordinates, and but this Poisson map is for surfaces with boundaries. But what happens that we observed that if you just combine two such things, like if you take torus with one hole and another torus with one hole, then our map also survive under gluing construction, which is kind of new observation. And it's not clear how to extend it for higher genera. Let me probably start with discussion what is cluster structure here. So what we're trying to achieve here. The question is, assume that we have a surface with a boundary, and the question is how to parameterize hyperbolic structure, hyperbolic metric on the surface, on two-dimensional surface, if we have boundary. So this construction is pretty well known. There are nice coordinates for that. Idea is that we cut the surface into something which is called ideal triangles. So the triangles whose sides are geodesic curves with respect to the chosen hyperbolic metric. So if we have holes here, so our geodesic look like something like that. This is boundary. Yeah. No, it's if we have boundary, so we have and we can triangulate our surface in such non-crossing collection of geodesic.
Boundary is always geodesic. Is the boundary always geodesic?
Boundary is always geodesic. Yeah, we consider the case.
You said idea triangle. So this means that these triangles are actually infinite.
Ideal triangulation means that the length is infinite.
Yeah, that's right. Yeah. So if we take what's called if the surface is hyperbolic, so the surface can be obtained by the quotient of this upper half plane by some action of Fuchsian group. It's very well known, and under this uniformization map, from Z to Z, our geodesic look like half circles, and they go to the points on the absolute.
Sorry, but this picture seems to be for surface without boundary.
No, it's for surface with
Где
boundary.
границы нарисованы? Границы.
Boundary is something like that.
It's not the whole H then. It's some subspace of H.
Subspace of subspace of it. Yeah. I don't know how. So, okay, and what I want to say is that kind of we split our surface into collection or into union of these ideal triangles, and not the following things, that all ideal triangles are isometric to each other. So now if we try to so ideal triangle is kind of rigid object, and our surface depends only on the way how we glue these ideal triangles to each other. So
А сколько штук самый маленький треугольник может быть?
it can be computed. I don't remember at all. No, it's finite number, like 3G plus 6G.
Вот так, ну
Some,
как
yeah,
линейный.
Riemann-Hurwitz formula tells you how many triangles. So, and this gluing part, well, we have to remember that if you take two Euclidean triangles with two sides kind of the same length, then there is unique way to glue this triangle such that sides fit. But since it's ideal triangulation, our sides have infinite length. So we can slide one triangle with respect to another one. So we can kind of, this situation or this situation are two different kind of, there is one parameter which describes how we glue two triangles together. And
One
this,
per H? One per H?
yeah, one per H, right? Because H corresponds to gluing two triangles. And this parameter can be described in different ways. It's called shear coordinate. It was invented by Thurston, I think. Like Thurston the elder. Yeah, like, I don't know, 40 years ago. And one way to kind of to see what it is the following. So,
Прости, а по-русски как называется этот параметр?
shear coordinate.
Thank you very much.
So one way to describe it is the following. So you have, let's draw these two triangles on upper half plane. So we get something like that. And we see that endpoints of our ideal arcs are just 4 points on absolute, so on real line.
Cross ratio.
Yeah, we can make cross ratio, but very specific, in very specific way. So if you just take 4 points, there is 6 ways to do cross ratio. Let's follow like Volodya-Fock genius invention and decrease the number of cross ratios. To do that, notice that we want to assign cross ratio to diagonal of this thing. So let's put 0 at one endpoint, infinity at the second endpoint, and one of the remaining one we assign -1. Then the value of the last point is z, and it must be positive because it belongs to the kind of, it's on the other half of the diagonal.
In your picture, the leftmost point must be minus infinity.
I don't understand the difference between minus infinity and plus infinity.
V1. It's on the V1. V1.
It's RP1.
Это абсолютно.
Okay, so yeah, I probably understand confusion.
Должно быть RP1, а написано было R.
Yeah, sorry, yeah. Yeah, so then we assign this parameter z to the diagonal. Well, ancient theorem from ancient Greek times that the collection of these parameters give us coordinate on the corresponding Teichmueller space, which include like kind of hyperbolic matrix and also prescribe the length of the holes, like on the boundaries, geodesic length of geodesic boundaries of the surface.
And how does this z related to this shear parameter?
Okay, so
It cannot be
in
directly.
whole honesty, the ancient shear coordinates are logarithm of this z, and z are exponent of the nature of kind of correction. Yeah. Okay. So now what is the meaning of these parameters from Pуассоновой point of view? Well, remark that, as I said, this Teichmueller space is equipped with something which is called Goldman-Poisson bracket. And it is some symplectic reduction. It can be described probably in most simple way as symplectic reduction of symplectic structure on the space of connection, but well, it does matter what it is, so we just assume it's kind of classical thing. So, and the meaning of this parameter is that it's very easy to describe the Poisson bracket in terms of these shear coordinates that we introduced. Namely, what you have to do, so if there is your triangulation, do we have colors, Chuck?
Yeah.
No,
The color?
it's big colors. So we can draw some. It's in English. It's called medial graph, kind of in difference from median graph. So you just take new.
In Russian, средневековый.
No, it's I don't know what's. You just take middle points of the edges and then connect them like such that in each triangle the orientation is what? Anti-clockwise.
Комбинаторный. Комбинаторный граф.
Combinatorial graph, Then now each edge is equipped with some our parameters. Let's call them z, ze, z, a, and so on. And the Poisson, this Goldman-Poisson bracket, ze, za, Goldman, is written as some constant times product z. So very simple formula. It's in particular if you take logarithm of ZA, then it just becomes constant. Now what is epsilon? Epsilon which depend on choice of EA. Epsilon EA, it is just number of arrows from E to A minus number of arrows from A to B.
Ну, это же не изначальное определение.
No, it's...
Это просто ее такое свойство, что в этих координатах она так
Да,
записана.
да, это свойство.
Это уже какая-то там, не знаю, фокусщина там.
Да, это фокусщина. Да.
Сейчас, простите, а на рисунке нет Е и А.
А?
А Е и А на рисунке нет.
Есть,
Есть.
есть.
Вот, например, на этой картинке. Okay, for example, on this picture, Z is equal to negative Z product Z. Because there is one arrow from ZA to ZE. If you plug it into this formula, you'll get 0 minus 1.
Простите, пожалуйста, это уже пример или там скобочек не хватает? Нет, последняя формула.
Последний это пример.
Пример. Example. Вот.
А, нет, ну там, да.
G.
Есть слева.
Нет, я думаю, слева не стоит.
Okay.
In
Now-
this situation, this number is not plus or minus 1. Is it possible to have Xi not plus or minus 1?
You mean
Ты так нарисовал, что кажется, что стрелочек может быть максимум одна.
Нет.
Ну,
Yeah.
вопрос в
Yeah.
этом.
Very nice question. Let me draw you beautiful picture of analysis.
Да, у вас они неизбежно сложатся.
No, it's even before that. So we can draw such picture. Then let's draw arrows between this arc and this arc. So if you go like anti-clockwise direction, so you'll get such arrow, and then rotating from that one to that one. Oops, the other way around. Yeah. So we'll get 2. So you are almost right. So the value of these epsilons can be 0, plus minus 1, or plus minus 2.
Сейчас, а я не понял, зачем второй треугольник? Там другая точка какая-то.
Сейчас, какой второй треугольник?
На левой картинке вроде все в правом треугольнике, да, обе точки?
Да, но как бы это часть большой картинки. У нас много треугольников, и мы рисуем этот граф и считаем.
У ZE не нулевая скобка не только ZA, а со всеми другими вершинами, с которыми он соединен стрелкой.
Я просто пытался нарисовать большую картинку, но после 2 треугольников устал. Okay, so now this is nice parameters. What is more nice about these parameters? So if you have, we notice that our parameters assigned to geometric picture, to triangulation of surface, to the arcs of triangulation. If you have triangulation, then you can do combinatorial transformation of this triangulation, which in English is called flip, and in Russian is also called flip. So, and under this transformation, if you write parameters x, a, b, c, d, then it's not very complicated computation that the parameters change under the flip in the following way. So x becomes 1 over x, b is multiplied by 1 plus x, c is multiplied by x divided by 1 plus x, d is multiplied by 1 plus x, and a is multiplied by x divided by 1 plus x.
And those 5 букв, это Z,
Yeah, it used to be z.
И вот они, эти Z, это
Да. And you can notice that the advantage that it's very simple formulas.
Сейчас, а зачем, почему должно быть такое преобразование? Это что,
Если мы пытаемся описать ту же гиперболическую структуру, но относительно другой триангуляции. мы пытаемся описать гиперболическую метрику с помощью выбора параметров. Этот выбор параметров зависит от выбора триангуляции, который мы нарисовали. Если мы изменим триангуляцию, то мы получим другой набор параметров, описывающий ту же самую гиперболическую структуру. И можно посмотреть просто, как меняются вот эти двойные отношения, и из этого получить вот эти формулы простые.
Мне все хочется спросить такое, вот если у вас есть два треугольничка, то можно провести вот эту вот линию, которая отсутствует, когда наоборот, вот этот четырехугольник, можно вторую диагональ.
Да.
Да, конечно, это вот оно и есть.
Я понимаю, но вот если это все на одной картинке сделать,
Да.
Да.
то тогда получится, что между этими двумя диагоналями есть угол.
Да.
Корректно определенный. Так сказать, он через Z выражается.
Да, выражается.
Ни в чем. В этом вопрос. Вот так. Это не хуже. И не лучше.
Okay, so and this is our dream. This is what we want to achieve, more or less. So we want to assign to Teichmueller space kind of without boundaries coordinates like that. The coordinates are described by some combinatorial object, like triangulation in the case when we have boundaries. And transformation, first of all, we want to look for the properties that the Goldman bracket has nice expression in terms of these coordinates. And if we do some kind of transformation of coordinates, combinatorial transformation of coordinates, then we have simple transformation formula for it. So the problem with closed surface is that we don't know how to start, because we don't have triangulation, we don't have natural triangulation that we can use. Here we consider triangulation which approach infinity. So it was essential for us that our triangulation kind of approach absolute in the right way. So if it was approached by
what is wrong if you forget about this condition? What will be wrong?
everything.
Just take
No, first of all, it's not clear how to assign parameters. Well, for example, what one can do, one can take pen decomposition and assign Fenchel-Nielsen coordinates. They describe Fenchel-Nielsen coordinates, you know, it's like length of geodesic and yeah. So the problem is that, first of all, transformation is not unique. If you have one pen decomposition, and you can transform it in many non-elementary, many ways to another pen decomposition. There is no analog of this flip thing. And second, the most important, the Goldman bracket also has nice expression in terms of Fenchel-Nielsen coordinates. That works. But substitution formula, the exchange formula for parameters are complicated. They're not as simple as that. So, and it's what they don't have cluster structure, and it's what we kind of trying to achieve.
И даже если возьмешь для рода 2, там что у тебя 6G, это вещественная же штука, да?
Да.
У тебя 6G минус 6, да? Значит, у тебя будет 6.
Нет, там сложные формулы переходят.
Если вот эти Фенхель-Нильсон, то непонятно, как можно было бы их вот...
Непонятно, да. Там сложные формулы переходят. Okay, so why do we need that? Because this is part of kind of more general settings of cluster algebra, which I don't want to explain because it will take another 2 hours. And for example, if you want to quantize it, so these formulas are nice. These transition formulas written somewhere here, it's nice for quantization, so we can construct the corresponding quantization of Teichmueller spaces and so on.
Well, once your bracket is algorithmically constant, it's already assigned that quantization is easy.
Yeah. But you need also...
This transformation property, I understand.
Yeah. Okay. No, you use this explicit way because you have. Andrei, sorry, I just comment. So, if you have chart, the quantization is easy, but you have different charts. And quantization in one chart should be compatible with quantization in another chart. And for that, you have to use transition formulas. So it's important to keep those.
Yeah, it's important that here they are rational.
Yeah. Okay. So surprisingly, nobody knows how to do it for closed surfaces. It was approached by Bondalom, who suggested the following clever idea. So, clever idea is the following. So, if we don't have boundary, but let's introduce this boundary artificially. So, let's pick up one point and say that it will be cusp of our, like singularity of our metric. And then we can do triangulation and play this game. But so we will get some parameters, but these parameters already they remember that you have some singularity. So how to remove this singularity?
So triангуляцию, которая одна вершина, да?
Yes, we can do that. It's not. Yeah. So, but we will require the following: that if you have cusp, and if you go, like if you take monodromy around the cusp, we require that this monodromy is identity. Then the singularity is artificial, it can be removable. Well, monodromy, we have like PSL2, the group is PSL2, it's element of PSL2. So the condition that element of PSL2 is identity, it kind of decouples in two conditions. First condition is that eigenvalues is 1. Both eigenvalues should be equal to either 1 or minus 1. This is a simple condition. It's condition which is Casimir in the corresponding bracket. And second condition that even if eigenvalues is 1, then we have this element which is not 1, which can be non-zero. And this element is already non-Casimir with respect to Goldman bracket. So we have to do. So if you want to use this approach, we have to do, how it's called, Hamiltonian reduction by this non-Casimir condition, which is complicated, and it was successfully done only for torus with one punch. Otherwise, it's just kind of formulas become too complicated, so he was not able to do that.
Вот это же у тебя будет какое-то условие кластерных координатах, что какая-то из них равна минус единице.
Типа того, да. Но да. Ровно то, про что Миша изобретал. То есть Миша Вейнстейн, вот, примерно
Нет, это в другом контексте, мы все понимаем, но почему, значит, в чем еще раз сложность?
Сложность в том, что sorry, I just short comment, not in official language. Сложность в том, что это выражение не Казимир, и оно довольно сложное, и ты по нему должен реализовать. Гамильтоновую редукцию по какому-то сложному выражению.
Проблема была в том, чтобы наложить, его можно наложить хорошо только в какой-то карте.
Правильно, да. Вот.
И вот выбрать эту карту,
да.
это...
Да. Ну, здесь что-то аналогичное этому. Вот у нас там нечто аналогичное этому и происходит. Но как бы Бондалом, когда это делал, у него не было. Бондалом, Фрэнсис Бондалом. Ну, как бы у него было выражение, которое там довольно длинное выражение. Ты его выписываешь, а потом должен сделать по нему гамильтоновую редукцию. Это сложно. Он справился в простых случаях, но сложных не мог. Okay. So I hope I explained what is the goal for.
I understand that it cannot be identity if all the parameters are positive real numbers.
Monopoly is not identity if all the parameters are positive real.
Analytic continuation of this picture.
Analytic continuation of what?
Of this picture. Glue ideal triangle.
Of doing the ideal triangles.
Yeah. If you actually glue a bunch of ideal triangles and
if we glue a bunch of ideal triangles,
and the combinatorics tells you that this is one cusp, then you cannot get rid of this cusp.
and the combinatoric guarantees that there is one cusp, then we cannot get rid of this cusp.
Yeah, that's true, yeah.
Do you mean that like some kind of analytic continuation of this picture?
Yeah, but you might consider analytic continuation and consider like different chart, it's not. No, but you're right. If you consider positive parameters, then you cannot get rid of it. Because, more or less, because this expression is just sum of Laurent polynomials is positive.
If you have positive, that's what I listed. In our case, these variables in C star, and still we have some problems because of this dividing
Exactly.
by 1 plus x or whatever. But what I understand what Roman says is that here we have just real positive, and then simply the condition that something equals -1
No, but
does not exist in any chart. So you have to continue.
No, but you can do analytic continuation and consider different chart in which the condition is satisfied, or do some more complicated stuff. But it's complicated. So, okay, what I want to say is that it's still complicated. So we don't do that.
Прошу прощения, там помимо вот этого искусственного каспа, ты объяснял, что еще есть другой способ. Можно, например, крендель склеить из 2 торов с дыркой каждый.
We coming to that. We coming to that. Okay. Okay. I hope that I explained what's the goal of what I try to present. Now we can forget about whatever I said and consider this algebraic part, symplectic gruppoid. And I don't think I will torture you with motivation, and just tell what it is. So let's denote by AN the collection of real unipotent and by upper triangular matrices. And then by symplectic gruppoid, well, idea is that we understand such matrix not as a transformation, but as a upper triangular bilinear form. Now, symplectic gruppoid of upper triangular matrices is the following: this collection of pairs B such that A is this unipotent upper triangular matrix, B is some non-degenerate invariant matrix. Yeah, everything is over reals. And we have extra condition that if you take BAB transpose, the result is also a unipotent upper triangle. So one can say that we have these unipotent upper triangular forms are sort of objects of our gruppoids, and this matrix B gives us a morphism which act on this object if you do change coordinate given by matrix B, the result is still unipotent upper triangle. Only such morphisms are allowed for this object. Results.
The transform value form, this value form is not symmetric.
It's not symmetric, yeah.
No.
Neither symmetric nor anti. Well, such definition was introduced by Bondalom, and for him, the model for this bilinear form was Euler form from derived categories. So, which is, as you know, much better than I do. So,
какая у этого размерность?
Двойная.
Good question.
Ты же мне говорил, что удвоенная.
Сейчас.
У этого, того, что внизу, такая же
Внизу,
в разу больше.
So, couple of statements. Well, important statement is the following: the dimension of M is twice the dimension of AN, and if you want numbers, you have to compute. And second important result is that
что ты не Гаусс, не можешь считать
как-то нужно считать треугольник, площадь треугольника, это сложно. Also, M is smooth. Yes, second result by Bondalom says that M is smooth, which is important. Again, Boндalom's result says that M has a natural symplectic form. For omega, which satisfy several properties. And let's denote by M2 fiber bundle, fiber square of M, so it's a collection of two pairs which are compatible. So it's two elements of M. Each element of M is such a pair. So if you think about A as an object and B is a morphism which can act on A, then the object of the second pair is the result of B applied to M. So it's kind of it's just collection of pairs which are compatible in the way that you can do composition.
Who is C?
C is another thing which is compatible with this object.
So it's B squared, A.
Just
So-
CB, ABT, CT is also upper triangle.
Yeah.
Нет, B
Thing.
нет. B не обязательно.
C, B,
B by C.
transpose, C transpose
Общую С, да? Тоже с таким же условием.
is also is unipotent upper triangle. Okay. We have the following periods. First, we have two projections. from this M2 to M, like we have projection on the first factor and on the second factor. And also we have multiplication map, so which take element from M2 to M, we check like following. So this pair C, B, A, B transpose, B, A maps to C, B, A. So you can do composition. And our form omega has the following property that if you if you kind of, they are compatible, that if you take pullback of omega by M, it is sum of pullbacks of omega by P1 plus pullback of omega by P2.
This is what is called Weinstein's.
Yeah, exactly, right. So, but Bondalom has concrete realization, how to compute that. And his idea was more or less, I'm not going to explain by many reasons, but one kind of idea is the following, that this space omega is somewhat isomorphic to cotangent bundle of AM. So there is linear projection which kind of identify this space of pairs with cotangent bundle to the space of unipotent upper triangular matrix, and you can just take symplectic form from here and pull it back to M.
But this projection does not coincide with either of these terms. This projection is not one of these two.
This projection from M to AM is not just forgetting B.
No, it's projection from M2 to M.
No, see here, you say M is projection bundle. So projection bundle has projection to A.
Yeah, projection.
Yeah. Forgetting B.
Forgetting B.
So you claim that from given A, all possible B's form just an affine space.
Yeah.
А как это связано вот с этой твоей умной формулой про M со звездочкой?
Никак. Ну, как бы способ, как это посчитать. Можно написать явные формулы. Вот это вот явно можно описать. Здесь
все-таки какое строгое вот определение?
Да, нет.
Это что
Но я...
Нет, они же насчет одной размерности, да, штуки?
Да, они одной размерности.
But only in algebra, right?
Чего?
Algebraically, in two-dimensional bundles for small transformations.
Леня, извини, я не слышу. Можешь еще раз сказать?
For small transformations for infinitesimal periods that are close to identity.
No, I'm not saying that it is close to identity. It means that they're homeomorphic. You object that they are homeomorphic or what?
No objection, just to say that we have something more than just this.
Okay, well, anyway, so let me probably go ahead, otherwise I don't have, there is no option that I will finish. Okay, so now what I want to say. So we will use this symplectic form on M to define the Poisson structure on the space of unipotent upper triangular matrices. So namely, we take Poisson structure on M dual to this symplectic form, and now we can consider projection, which take pair PA to A. So which is a map from M to AM. and take the push forward of the corresponding Poisson bracket here to an. Claim it's non-trivial statement that the push forward is well defined here, and it gives us nice, well, some Poisson structure on the space of matrices.
But then it can't be true. The first line cannot be true.
Why?
No, nobody said that.
If you just take potential boundary project to the base.
No, it's I take my words back. It's not forgetting. This is forgetting.
Okay.
There is some formula which kind of. It's very algebraic example. So if you have n equal 3 and matrix xyz like that, then this Poisson bracket looks like that. So the Poisson bracket x and y is 1/2 xy minus z. Yz is 1/2 yz minus x, and zx is 1/2 zx minus y. So very well known.
Не, я имел в виду вот это отождествление в первой статье с кавычками. Там, наверное, что-то неукрытие происходит.
Не помню.
Ну да.
Okay, so if the specialist in integrable system probably can recognize that it coincides with the Poisson bracket, which appeared in work by Dubrovin and Ugaglia on the space of azimonodromic deformations. So if you take Stokes data, then azimonodromic deformations can be written as some Hamiltonian flows with respect to some Poisson bracket, and in terms of Stokes data, this Poisson bracket is exactly like that. And anyway, so there is kind of, let's call it Boндалом Poisson bracket on the space of unipotent upper triangular matrices. Now, what is known about that from Boндал's work?
В данном случае это будет результат вот этой твоей процедуры.
Да.
Что если вот взять не эти матрицы, а вот там ТС-звездочки к ним, или вот это М, значит, на нем что-то такое написать и спроектировать, то уже на этих матрицах, до этого она была тривиальная, да?
Да.
Если ТС-звездочки, то...
Да.
А теперь она станет вот такая нетривиальная.
Извините, пожалуйста, а много таких брикетов, то есть форм, как омега, которые удовлетворяют такому условию?
Я думаю, бесконечное число.
То есть он построил просто какую-то такую?
Да, он построил некоторую конкретную.
А она чем-то еще совершенно уникальна или просто...
Не знаю, считать можно. Не знаю.
А вы прям не расскажете, как ее делать?
Ну, можно я не буду?
Можно.
А почему ты думаешь, что это бесконечно много?
Я ссылки могу прислать.
А почему ты думаешь, что это бесконечно много?
Ну, так вроде это условие.
Ну, собственно, любое число можно умножить.
Ну, не знаю.
Она для других К тоже будет такая же, как каноническая с такими линейными поправками?
Для других М.
Для других, ну вот там К равно 3 написано.
N.
А, это N.
Да, она всегда выглядит как квадратичная с такими линейными поправками. Но не лог каноническая. Квадратичная часть для больших n не будет лог канонической.
И тут с этой стороны второй.
Одна и вторая не мешает.
Стрелка не рисует.
Да, значит, окей. what else do we know? That we can describe Casimirs. Casimirs are given by the following: that if you take A plus lambda A transpose and take determinant, it's polynomial in lambda of degree n, and this polynomial is reciprocal. I forgot how it's spelled. Meaning that возвратный полином.
Palindromic.
Is it palindromic? Okay, palindromic.
Слушай, у него начало такое, что хвост, да?
Да. Коэффициенты симметричные относительно. Okay, so and coefficients are basis of generators of Casimir algebra. So coefficients give independent Casimirs. So totally we have a floor of n over 2 independent Casimirs.
How did you get it? From the symplectic on teacher.
How do you get Poisson bracket on A, n?
Yeah. From
A, n?
By projecting this mysterious omega slope. Omega inverse from n. No explanation.
Yeah, so we take dual Poisson bracket, dual to omega Poisson bracket here on M and take push forward by projection.
As a vector field.
As by vector field, yeah.
This map is
Birational? No, it's from. It's like an equal system.
No, it's not birational.
How can
It's
you
half dimension.
how can you push
Forward.
yeah.
Descent. The claim is that descends to.
Yeah, it's statement. It's not obvious. You have to compute. It's not obvious.
Берем две функции на образе, от них мы можем взять полбет и взять скобку Пуассона. И она вдруг окажется тоже полбетом некоторой функции. Это некоторые совпадения.
Okay. So now we want to find good coordinates for this symplectic gruppoid. Now, what does it mean, good coordinates? It's, as I said, it's something like Darboux coordinates. Let's give the following definition. Functions fi form a log canonical system if Poisson bracket f alpha f beta is equal to some constant dependent on alpha beta times f alpha f beta. And so we want to find something like that for in this symplectic gruppoid situation. If you look at this example, you will see, so if you forget about linear part, it's this xyz is almost what we want to get. But this linear part, it's kind of, it spoils the form. Okay. Now, how one can do that? Let's ask the following question. Question: given B, find A compatible with B. Well, compatible in the sense that B transpose is unipotent operator. Well, how much time do I have? Okay. Minus an hour. Minus 1 hour.
Well, it's you see, we are not in the standard situation. We started much later. Yeah, but well, I think we have half an hour.
Half an hour. Okay, then I will skip half of the talk.
How much time did you plan?
And explain the following. So, first of all, this question can be not for any B, we can find A. And second, if we can find A, then it's unique. Now let's describe condition. Let's describe the set of B's for which we can find A.
В находится A, да?
Да. У нас есть GLM, мы берем из B из GLM и смотрим, можем ли мы найти для нее соответствующее.
А вы нам говорили, у него размерность гораздо меньше, чем у GLM, да, у этих B.
Ну, B примерно такая, у пары.
А у GLM гораздо больше.
Нет, примерно такая.
Где ты на этом? Не, сейчас. Вы что-то там на
A размерность половины. Значит,
сейчас у B размерность такая же, как у А, да? Как у АН.
Если мы фиксируем А, то у соответствующей B размерность такая же, как у А.
Ну, то есть этих B, вот, для которых такое можно найти. Сейчас
сейчас.
В общем, их тоже мало. Короче говоря, понятно, что не все живет.
Не все живет, да. We're trying to describe B for which such pair exists. And answer is the following: that if you take B, if you take block decomposition of B, such that it's K by K, and this is N minus K by N minus K. So let's denote this BK, and this is Bn minus K. Then A exists if, so, well, okay, let me say true statement that if a determinant Bk divided by determinant Bn minus K is equal to -1 power n minus 1, and determinant B is equal to 1, then A exists.
For any K?
For any K, thanks. From 1 to 1. And moreover, this A is unique. Well, it's more or less, if you think about that, it's more, I wanted to show example, but because of the time restriction, I am not able to do that. But A is determined by the system of linear equations, so it's kind of, it's really simple statement.
It's not if and only.
It is if and only if.
No,
no, it's not only if. Yeah, there is. It's kind of one connected component of solution. It's why kind of this -1 is not But it describes one connected component of solutions. So now why I'm saying that, because again, for people in integrable system, I think this is very recognizable function. Those are just Casimirs of the standard R matrix bracket in GLM. So what we are saying here is the following: that if you take the standard trigonometric R matrix bracket on GLM and квадратичная скобка.
Квадратичная, тригонометрическая функция не есть квадратичная.
Ну, whatever. Матричная скобка. And we fix some particular symplectic leaf of this bracket. Then for any matrix P in this symplectic leaf, we have a solution of this problem. So this symplectic leaf is basically birationally equivalent to symplectic gruppoid. Well, this is not obvious, but it's what can be computed. That if you take if we denote by GL not symplectic leaf.
Он же другой размерности. Это, конечно, твой группоид это А и Б вместе.
Да.
А здесь ты говоришь, что симплектический лист это только то, что часть Б заказала.
Да, но А единственное. По Б А восстанавливается единственным способом. Поэтому.
Сейчас, казалось бы, если Б единичное, то не единственное.
Ну, это как бы такое бирациональное отображение. Да.
M отображается в AM, это проекция, которая уменьшает размерность вдвое, но M можно отобразить наоборот в GLM, в первой проекции. И это вложение к размерности M.
Да.
Ну почти что.
Да.
Бирационально.
Единичное вроде не может быть с этим условием.
Но мы же знаем, что оно...
Но единица не описывается вот этим.
Ну, мы только такие.
Да, здесь некоторое такое тонкое место, но это бирациональная вещь. Okay, so what I want to say that this is kind of Poisson equivalent, birationally Poisson equivalent to R. But cluster coordinates for these things are pretty well known. These are given by so-called Fogg-Gonchar parameters, and now we can use these Fogg-Gonchar parameters to describe the corresponding coordinates. Let me try to do it briefly. So next chapter is Fogg-Gonchar parameters.
Это на жиле.
So I will just draw some picture, and I will put parameters on this picture, and then I will explain how to make matrix out of these parameters. So we start with the following thing first. This is example n equal 3. So let's draw a triangle, and then let's make the following directed graph. It's a triangle and directed like that. So all directions goes right to left and bottom to top.
Это значит, что треугольник или трехходящий, то исходящий? То есть если 4, это что
Вот
будет?
что-то там с
Будет 4.
Нижние
Нижние
стрелки,
стрелки.
с нижними стрелками это не так, хотя они должны быть вверх. Если все вверх, то что пересекает нижнюю линию.
Но последняя стрелка получается.
Да, это неприятно.
Нет.
Такая неприятная.
Ну, давайте.
Извини, а как-то вот это дело, здесь же вроде о группе желез идет речь.
Да.
То есть вроде согласно Гончарова, ты должен взять слово там в группе В или
Это эквивалентно стандартному слову.
Это эквивалент стандартному
Да,
слову.
да.
А какому?
Слово из 3 букв 1, 2, 3, 1, 2, 1.
1, 2, нет, сейчас. Это в железе.
Нет,
3.
извини.
Там никакой 3 не может быть.
Нет, извини.
Ну, значит, это верхнетреугольные, ну да, это значит, что типа просто 1, 2, 1, наверное.
Это 1, 2, 1, да.
Нет, вы можете объяснить, что вы такое говорите?
Может, не надо.
Я объясню про 1, а кто пишет, объясню про 2.
Это же
Maybe it's better not to explain this 1, 2, 3, but let's just concentrate on this picture. So, what Fock and Goncharov did, they put parameters in faces of this graph. So let's take parameters and label these faces, how it's called? I forgot this word. So this is Z3, 0, 0, Z2, 0, 1.
The eccentric coordinates.
Barycentric, yeah, exactly, barycentric indices. And this is Z1. Okay, so I hope it's clear how it works. So these Z's are just some parameters which stays here, just some numbers.
А там еще тоже что-то сидит, да? Вот где ты меня нарисовал.
Да, везде сидит, везде сидит.
10 координат.
It's homework. Okay, now let's take any oriented path. For example, like this one. And to this path we assign a weight. So weight of path is just the product of all parameters above the path. Now let's label I have parameters. I want to construct upper triangular matrix from these parameters.
А вот там написан заголовок.
For Goncharov parameters on GLM.
Так, а какое отношение к картинке имеет? То есть потом...
Okay, so I start with this picture. I introduced what is the space of parameters for this triangle.
Их 10 штук.
Их 10 штук. Теперь я некоторые параметры...
N равно 3, да?
N равно 3. Я некоторые параметры забуду, а из оставшихся сделаю верхнетреугольную 3 на 3 матрицу. Но уже с единицами на диагонали, то есть у меня будет 6 параметров. А потом я возьму другой треугольник, такой, и сделаю похожую картинку и еще построю нижнетреугольную матрицу. И потом я эти две картинки склею, и в качестве объекта я получу такое произведение нижнетреугольной на верхней, то есть полномерную матрицу, запараметризованную вот этими параметрами.
Ну их 10 штук тут, и там еще сколько будет?
Ну, их здесь больше, чем нужно. Я не все из них буду использовать, но мне как бы для дальнейшего будут нужны. Да. Okay. So now I want to construct upper triangular 3x3 matrix. Let's call Tij. The element of our matrix is the following. So you take sum over path connecting J to I, oriented path, directed path, weight of this path.
Это ведь ты делаешь что-то эквивалентное тому, что вот, по-моему, проще, если писать вот слово, как они пишут, из произведения нашей на Е, да?
Да.
И там ты с очевидностью получаешь верхнетреугольную матрицу, если ты берешь только Е.
Да.
Да? Но только по модулю вот этой диагонали, с которой все равно потом будешь мучиться.
Да.
Но ты вот таким ужасно сложным образом это описываешь.
Это зависит, знаешь, от воспитания. Если ты ходил в детский сад, где тебе объясняли вот разложение 1, 2, 1, то тебе проще 1, 2, 1. А если ты ходил в соседний детский сад, где картинки рисовали.
У меня есть другое объяснение, я потом
По построению получится верхнетреугольная матрица.
По построению получится верхнетреугольная матрица, просто потому, что этот граф...
Это даже делать такие.
Маленькие ученики детских садов.
Okay, so well, moreover, we can define in similar way. So we have upper triangular matrix which goes like from this side to that side. And now we have more parameters than needed because to define this upper triangular matrix, you notice that the bottom part is not used. But instead of, we will define three matrices. For each angle, we will define the corresponding matrix like this, which goes this way, and this way. And for triple of these matrices, we will use all parameters. And let's define, call them T1, T1 bar, and T1 tilde. Now the most important part of this construction, now we take the triangle pointing down. And for triangle pointing down, when I explain what happens when we consider this matrix T1, when we fix the corresponding kind of center of, I don't know how to, we select this point. So if we consider this point, we have to rearrange orientation. We keep parameters the same, but we have to rearrange orientation and kind of rotate the picture by 120 degrees and then do the same thing. Well, in similar way, we can do with triangle pointing down, and we get matrices T2, T2 bar, and T2 tilde. And T1, whatever. T1, T1 bar, T1 tilde, upper triangle, non-unipotent. And T2, T2 bar, T2 tilde are lower triangle. They also depend on different collections. Well, the same kind of the same picture, different collection of letters, but
10 дам дубль, может быть?
10 дублей.
Извините, что забыл. А это Не то же самое, что он на том треугольнике старом еще, Т1 в обратную сторону стрелкой рисовать.
Ну, надо все три стрелки.
Да, все три стрелки. То есть можно со старым треугольником просто стрелки в обратную сторону рисовать.
Да, и буквы, новые буквы Z только здесь.
Новые, а почему новые? Потому что независимые, потому что... все, понял, да, все. Новые буквы. Да.
Почему? Независимые на общей границе. Зависимые.
Пока нет. Пока не сказано было.
Сейчас скажу. Нет, независимые, да. На общей границе независимые. И теперь we can kind of combine them together. And so we have the following T1, T1 bar, T1 tilde, here we have T2 tilde, T2 bar, T2 bar. And let's introduce matrix S, which is kind of 1 and minus 1 going along the secondary diagonal.
Minus 1, они чередуются или сейчас?
Чередуются. 1, minus 1, next one, 1.
У меня какое-то жуткое ощущение, что ты вот что-то на группе строишь, на самом деле, язык конструкции для пространства модулей связанности.
Конечно.
А почему не взять сразу на группе, если нужно на группе, почему сразу на группе не построить? Открыть другую работу, тех же авторов. Ну, необыкновенная история.
Потому что не совсем получается на группе. Вот, через секунду я скажу. Потому что у нас получается нечто, что мы не можем...
Нет, ну ты здесь сказал, что это же симплектический лист на группе. И групповой параметризации почему-то не дается условия на резюмирование.
Ну,
а еще тут, потому что одновременно не только это самое Пуассоновая структура строится, но еще и удобная система координат, вот, каноническая.
Она на группе строится у них точно так же в канонической системе координат.
Да.
Вот единственное, что можно предположить, что вот эти условия на резюмирование плохо накладывают, да?
Мы сначала...
Взять,
потом наложим условия
на группе написать, то вот эти условия накладывать неудобно. Что-нибудь в таком духе.
Ну, как-то...
Или если ты говоришь, что это больше, чем на группе, то скажи на чем.
Это больше, потому что группа, как бы матрица B здесь вот такое произведение, T1 на T2. Когда ты это вычисляешь, то ты здесь не учитываешь некоторые параметры. Мы как бы по нашей конструкции мы сначала их учитываем, а потом от них избавляемся, и так получается для нас почему-то удобно. То есть то, что у нас получается, на самом деле неожиданно как-то намекает на то, что мы изучаем плоские связности в каком-то виде. Я не совсем, не знаю, плоские что-то, но на неориентированных поверхностях. Это получается из формул, которые мы здесь получаем. Как бы у Фока-Гончарова поверхности ориентированы. Они изучают плоские связности на ориентированных поверхностях. Здесь, когда мы, ну вот, сейчас можно я напишу? Да. Okay, so remark. Now let's introduce Poisson bracket on these parameters. This Poisson bracket on these parameters look very simple. So what we have to do, we have to draw dual graph, kind of which look like
maybe different color.
Yeah, something like that. And we have arrows of two types. These dashed arrows mean that they have weight 1/2, and solid arrows mean that they have weight 1.
А в соседних треугольниках они как взаимодействуют? Вот там, где склеены.
They commute. Parameters in neighboring triangles, they completely commute. And what we want to do, we will write the formula formulas for matrix A and B. So A is equal to T1 inverse S T2 tilde T1 transpose S, and B is T2 T1. Okay, if you go back to this picture, then what happens here is the following. So B is composition of kind of some sort of monodromy which takes something on the right side to the left side. It's composition to one parallel transport and another parallel transport. From this side to that one and from this side to that one. Now, it's not quite clear how to make interpretation of that, but taking transpose of the matrix equivalent to changing all orientation of the oriented graph to the opposite one. And taking -1 correspond to just inverting orientation of horizontal errors. So, for example, this thing sort of vaguely corresponds to the following loop. We just start from this side, go down, then glue the kind of this side to the top one. Glue in the following way, so kind of with changing orientation. For example, this point is glued to that one. And then going back like that. So it's, what we obtain is sort of flat system on Möbius strip. Because you take rectangle and then you just glue two opposite sides of rectangle, changing orientation. The result is unipotent upper triangular matrix. It's easy to see from this formula that it's unipotent upper triangular matrix.
And is it possible to proceed as you described? So if you constructed B in such way, then after you impose these conditions,
yeah. So this is forget about unipotent. This is upper triangular. It's not unipotent. And B transpose is also upper triangular. So if you forget about condition unipotency, so we will...
Вот прямо вот эту верхнюю формулу можно найти, как я говорил, путем решения линейного уравнения? Или вы просто угадали?
Угадали.
Is it clear that this is upper triangular?
It's more or less clear, yeah. Well, S, this conjugation by S sort of change upper triangular with lower triangular. T1 transpose is lower triangular, T2 is lower triangular. So this part is lower triangular, you conjugate by S, it will be upper triangular, and then you multiply by another upper triangular. So the result is upper triangle.
А если это матрица 3 на 3, да?
Нет, это для любого размера. S, да, S это матрица N на N, но...
Правда, что это S переделывает F в E транспонированное, да?
А у вас разве не 3 на 3 случай?
Как? Ну, пока нет. Пока.
Вы же говорили, n равно 3. Я писал во всей этой истории.
Для n равного 3 S будет такая, 1 минус 1.
Сейчас, да. Ну, а это что?
Да не правда, что она переделывает сопряжение E транспонированное?
Нет, сопряжение S делает центральную симметрию относительно середины. Это не транспонирование. То есть этот элемент переходит в F.
Но я это примерно и пытался.
Нет, но этот элемент переходит в F. Это не транспонирование.
Но они в E и в F эти все единицы.
Но верхний треугольник переходит в нижний треугольник.
Верхний треугольник?
Да, это правда. Но это центральная симметрия, это не транспонирование. Это не осевая симметрия, а центральная симметрия.
Скорее E минус 1 тогда.
Ну,
у нас же заголовок, подзаголовок, параметр формы Горчарова на GLN, поэтому за можем и не следить. Нам достаточно только за B следить.
Ну,
Это вот примерно так.
Ну, вот
видишь, B такая нормальная, это 2 на 1, а черти что.
Ну да. А потом, согласно предыдущему, А можно восстановить по B. И это вот в эту конструкцию, это восстановление вот таких вот
еще нет, потому что у нас не унипотентные матрицы.
Ну потому что же n больше, чем m.
Надо убить вторые некоторые.
Нет, тут уже многое убито, но еще осталось диагональ.
Еще надо диагональ убить в этой конструкции. И что здесь? Вот we notice, when we write this formula, we notice the following, that if we express elements of A in terms of these parameters, then we notice that this guy doesn't enter, this guy doesn't enter the expression separately. So it's always entered as a product of this one by that. So it means that the bottom part can be glued to the top part with changing orientation. So you always have expression when you have product of this times that, or this one times that. And this is mystery. So we don't have conceptual explanation what happens, and but it reminds something like some flat systems or non-oriented surfaces.
I don't want to think it's a flat local system for non-constant local system of groups.
Groups?
Yeah.
It's a flat local system for
non-constant local system.
Flat local system for non-constant local system of groups.
So what
Flat local system for non-local system of groups.
For non-trivial, non-constant local system of groups.
Like you can do to sheet cover.
Yeah, that's right.
And this local system will become trivial. You can say that
Local system groups will become trivial.
Yeah, right.
And local system becomes the applied deck transformation.
Yeah, I think this is right. But we sort of
in terms of descent, it's called for non-trivial local system.
Окей.
Ты совсем заинтриговал, что тут у тебя какие-то неориентируемые, а в результате какие-то должны торы с дырками возникнуть склеивые в крейде.
Yes, but I'm on page 3 approximately, and I have 7 pages. So let me probably compress the remaining 4 pages into like 10 minutes.
Can't you continue next Monday?
Okay. Next Monday, what date is?
27-е, к сожалению, уже что обещал, там просто начинается одно другое наезжать.
Нет,
поэтому,
может быть, я могу быстро сказать.
Нет, нет, просто видишь, это знак, что люди хотят узнать. И это среда, к сожалению, уже не так.
Okay, so what I want to say, so we got sort of solution of our problems that we discussed before, but for non-unipotent matrices. Now, kind of, we live in the United States, we have Trump, and Trump says make non-unipotent matrices unipotent again. So we can introduce some restriction on the Casimirs of the function. And unfortunately, I have to skip it. It's not very complicated. There are lots of beautiful pictures, but it just takes time. So what I'm saying is that one can restrict ourselves to particular values of Casimir's of this space from these parameters. And then we will know that we will get a unipotent matrix A and some matrix B, which is solution of our previous problem. Now, these parameters by design are log canonical parameters of the corresponding Poisson bracket. I mean, these parameters. So, I promise you to provide a log canonical system for symplectic gruppoid. I'm done with that. So now the dull part of my talk is over. And I want to explain in the nice 5 minutes that remain what is connection with Teichmueller space.
Получается, что есть две Пуассоновые структуры, для каждой из которых мы провели некоторые вычисления и получили канонические координаты и, соответственно, матрицы.
Да.
А после этого формальная процедура, что у нас есть свобода применять кластерные преобразования. Мы применяем и там кластерные преобразования до тех пор, пока матрицы не станут совпадающими.
Ну да, более-менее так и есть, да. Но только мы их в одном месте применяем, а не в двух.
Ну, я хочу сказать, что, мы вот именно что мы применяем, пока не совпали, а если совпали, мы радуемся, а если не совпали,
если не совпали, то еще применяем.
Что нет никакого канонического способа.
Нет. Ну, то есть мы не понимаем. Окей.
Но там произвольное кластерное преобразование, там есть
нет, ну как, у нас есть колчан.
Там есть мутации не в четверных вершинах. Вот давайте просто.
Да, есть.
Тогда плохо.
Нет, ну сейчас.
Просто мутация в четверных вершинах это вот в такой конструкции на группе, это просто некие перестановки матриц.
Нет, Андрей, у нас здесь более, надо сказать, такая простая ситуация. Okay, so what I want to say is that let's now restrict to the case n equal 3. Exactly. And we describe cluster structure on the corresponding symplectic gruppoid. This cluster structure is given by Quiver, and yeah, I'm going to draw it. So, what this Quiver, better. First, I'm going to draw it here, like that. So it's so we have 6 parameters. Yeah, maybe let's go back a little bit and remind what we have. So we have GL3, it's 3 by 3 matrices. Inside this GL3 we have this
symplectic. В каких-то вершинах число входящих равно числу выходящих, а в каких-то нет, да?
Inside that we have symplectic leaf. So this is dimension 9. And so, if you remember, we have for 3 by 3 matrices, we have to impose 3 conditions. Determinant is equal to 1, and 2 ratios is equal to negative 1. Is equal to 1 also. So the dimension of this guy is 6. This is a symplectic leaf of the usual R matrix bracket.
А это вот сейчас это его колчан или нет?
Это его колчан, да. 6 параметров. Раз, два. Не колчан не вырожден.
Не вырожден.
Да. Those coordinates describe this symplectic leaf, and this Quiver describes the corresponding Poisson bracket So and one can check that it is non-degenerate. So it fits. Now we have the map that we described. So we have the map from GLN 0 to pair A tilde, where A tilde is this B, A, B transpose. Okay, meaning the following, that for B from this symplectic leaf, we can find uniquely the corresponding object A, and then we can take the kind of the image of morphism B applied to A. So for our case, it will be GL3 going to a pair of two upper triangular matrices.
Опять же, вот это вот GL3,0, это небольшая клетка в GL3?
Нет, это не...
Небольшая клетка.
Нет, это небольшая клетка. Нет, большая клетка размерность 9. Что такое большая клетка?
Большая, ну 9.
В смысле, это максимально симплектический лист.
Ну да, все корни без картана.
Да, это максимально симплектический лист.
И вот, то есть ты говоришь, что вот ее колчан может дебутировать вот в таком образе.
Да, вот наш первый результат в том, что мы можем ввести координаты на этой хрени, так что колчан вот имеет такой вид. Okay, so from this crane we have map from GL3 knot to pair A, so which is direct product A3 times A3. Dimension of unipotent upper 3 by 3 upper triangular matrices is 3. So here is 6, and this is 3, 3. It looks like everything is compatible. But I claim that the image of this projection is 5-dimensional.
Is what?
5-dimensional. So it's 1 dimension less than 6. How does it happen? So if you take for 3 by 3 matrix.
А запятая основной, да?
Yes, yeah, it's a pair of matrices, pair of 3 by 3 matrices. So let's introduce Markov element. It's just function of our 3 by 3 matrix, which is for matrix like 1, 1, 1, x, y, z is equal to x, y, z minus x square minus y square minus z square plus 4. And or in other words, it's 1/2 determinant A plus lambda A transpose, like that. So it is Casimir of our Puassonov.
It's lambda.
Oh, yeah, sorry. Yeah. No lambda. So it is a value of, no, sorry, I take this back. So nothing. So this is just this figure. Claim, very easy to check that M of A tilde, well, if we use this formula, it's 1/2 determinant B A B transpose plus B A transpose B transpose. Then we can factor out B and B transpose, so it's 1/2 determinant B squared times MA. And let's recall that in order our equation to be resolved, so we require that determinant B is equal to 1. So this is 1, and this is equal, sorry, like that. So this is equal to M of A. So the Markov function remains invariant. And it's the only condition. So it means that the image here is 5-dimensional. It's one dimension less than 6. Okay, now almost final remark. So now we're going back to approximately the same time as
the condition is MA equals MA2.
The condition is that, what is it called?
MA is
MA
equal to
of A tilde.
Yeah.
Yeah, condition is condition.
Yeah.
m a tilde equals m a. So a and a tilde, they are not independent, they satisfy this condition, so kind of it's not 6-dimensional space. The pair a and a tilde is 5-dimensional space. Okay, now let's go back to 90s, I guess. Folk, Chekhov construction. So if you take Teichmueller space of genus G curves with 1 or 2 holes, we can embed this, we can consider Poisson embedding of this Teichmueller space into the symplectic gruppoid. It's construction that was done by them like a long time ago. Let me probably. So what they did, they consider a very special ribbon graph. Okay, so n is the number of inclined edges. So here n is 4. Yeah, maybe really I'm probably overdoing it. So let me just do it for n equal 3. For n equal 3, it's the following picture. Oops. So this is the same as a torus with 1 hole. And if you have that, let's denote this inclined at edges by 1 to 3. And say gamma ij is a loop which goes along inclined hi and then comes back along inclined hj. For example, gamma 1, 2 is the following loop. Now let's define each loop corresponding, you can take the Fuchsian group element which correspond to this loop, and we say geodesic function Gij is the absolute value of trace of the corresponding element of Fuchsian group. Okay, so such thing, yeah, it encode.
Как-то не может так быть. У этого графа слева один край, компоненты края и там.
Да, здесь один край есть. Это торс.
Сколько компонентов?
Давайте считать. Это я подготовился, это я могу сделать. Давайте, вот начали отсюда, идем. Раз, два.
Я что ж вы прыгаете, вы не прыгаете.
Нет,
как?
Вот.
Ой, не, да,
не сюда,
виноват, да, это вы правы.
Прыгай, но тут надо другое место.
Понятно, что нарисуем.
Okay, so to parameterize the corresponding Teichmueller space, we assign to each edge one parameter, as we did before. So it's sort of dual graph to triangulation. Yeah, is it clear? Right. So we have like x, y, z here, and the collection of parameter x, y, z, we associate with the matrix 1, 1, 1, gamma g1, 2, g1, 3, g2, 3. Claimed by Fock and Chekhov is that if we equip this collection of parameters with Goldman bracket and this one with Bondalom bracket, this is Poisson map. So which take this Teichmueller space into some symplectic leaf of this Poisson metric. For n equal 3, it's kind of generic symplectic leaf. Really, it's kind of, well, it is at least it's local isomorphism here for n equal 3. Now, okay, so let's go back here. So what we get here. So we have GL3 0, right? Matrix B here. To matrix B we associate two.
Вот тот недостающий параметр это как раз то, что при склейке.
Exactly. So we associated two upper triangular matrices, A and A tilde. By Fock-Chekhov, we know that A corresponds to some torus with one hole. And by A tilde also corresponds to a torus with another hole. But we know that Markov function of this matrix is equal to Markov function of matrix A tilde. Markov function has geometric meaning. This expression, where I wrote this Markov function, here, it is the same as hyperbolic cosine of geodesic length of the hole. This is 2 and this is 1/2, but up to some, if you write it correctly, so it describes the geodesic length of the hole. So if Markov numbers are the same, it means that the length of this hole is the same as the length of this hole. So we can glue them together. But when we glue two such things together, we add one extra parameter of gluing, because we can take top part and kind of rotate it with respect to the bottom part. So two these guys separately are described by 5 parameters, but after gluing, you need 6 parameters to describe this construction. And we just computed that this thing, because of this quiver, is described by 6 parameters. So conjecture naturally is that we have we described this genus 2 surface after gluing. And we can check it. So I don't. So it's already too late. It's really the case. So, but this construction is. We can do construction. We can check that it is the case, but it's sort of very mysterious because we don't understand really what geometric meaning of these parameters. We don't have description in terms of triangulation or anything like that. We don't have. Well, we have some hints, but we don't know exactly we don't understand what cluster mutation corresponds to. Like in standard situation, cluster mutation corresponds to flips of triangulation. Here we don't know, we don't have triangulation, we don't know what we have to flip. But anyway, the construction exists. So question is, there are many questions here. So the biggest question is how one can generalize it for higher genera. Kind of, there is hints that one can do it for non-commutative parameters. So something like that should work. And there are many directions where you can generalize it. I think everybody fall asleep already. So. But I'm done.
Спасибо.